All right, guys. So yesterday, oops, my PowerPoint's being weird. We started section 1.7, looking at chemical properties of polymers. I'm going to go a little faster through this material today because, again, we need to get into Unit 2, and there's really not much material here that you really need to focus on from Chapter 1. So let me just check the chat. Oh, good afternoon. Um, chemical properties of polymers, basically the big thing to know from this section, I don't know why my keyboard's not working, section 1.7, is that the chemical properties of polymers are controlled by intermolecular forces. And that's really what you need to know. In particular, the hydrogen bonding. So we did this yesterday. I'm just kind of doing a review. The large size of these molecules means that they have very large and complex intermolecular forces. It's a lot harder than in 1120 when we did, something like water or ammonia or, I don't know, carbon dioxide. These are very, very complicated and bulky molecules with lots of functional groups and hydrogens and lots of interaction between them. So this slide here, very important. The intermolecular forces in polymers are typically affected by the polarity or dipoles. Okay, remember from I was going to say chapter 1. Remember from chemistry 1120, dipoles means that the molecules are polar. So because because polymers have lots of polarity in them, it can result in high tensile strength and higher melting points. So again, we did this basically back in chemistry 1120. High intermolecular forces means higher melting points. Tensile strength is the strength to pull something, so to the point where it breaks. So tensile strength is to pull until it breaks. Okay, so that's it. I'm going to move into the next section. This is really all you need to take away from section 1.7 is that intermolecular forces, specifically polarity or dipoles, means that polymers have high melting points, and it takes a lot of energy to pull it until it breaks. They're stretchy, they're tough, they're durable. Compared to like glass, think about, if you drop glass on the floor or you try to pull, well, I guess glass would have strong tensile strength if you pulled it. But what I'm saying is polymers are very tough and durable, and it's because of their polarity. Okay, so this is really it from section 1.7, and I'll move into section 1.8 if that's okay with everybody. And then we can finish off. So you don't need to worry about this stuff here. Okay, is that cool? Give you guys a little less things to know. I can't remember who yesterday mentioned, going forward, if I could really emphasize the slides that you needed to know. So there you go. All right, let's look at the last and final section. It's a very short section in Unit 1. Oops, and it's about the formation of polymers. So we're going to look at kind of how polymers can be formed, two main types of reactions, which we'll look at right now. So I talked about this before, I don't know when, sometime in an earlier unit. Polymerization is the process of linking monomers, so small carbon-based units, into a long carbon chain. So synthetic, which means human-made, polymers are created by joining the monomers together. So how do we do that? Well, think of chemical reactions in general. I mean, even think of like cooking. Baking or cooking an egg or chicken, that's a chemical reaction. So you can't just look at a chicken and watch it cook. You're not going to fry an egg just by staring at it. You need to do something to it. Typically, we add heat. That's a chemical reaction. The cooking process is a chemical reaction that is helped by heat. If any of you bake, I know I'm making you guys hungry again. If any of you guys bake, why do we put baking soda in the food? Well, baking soda forms carbon dioxide. So when baking soda gets wet, and when it's heated up, it forms gas, carbon dioxide. It's essentially a neutralization reaction. And the carbon dioxide produces gas, or is gas, so your muffins will rise. Bread is a little different because that's from yeast, but it's all chemical reactions. So what I'm saying is to make polymers, you can't just look at them. You need to, somehow apply a chemical reaction to this. You might have to add an acid or heat or a base. So the first type of polymerization we're going to look at is addition. Addition polymerization is a technique where monomers are added onto the active site of a growing polymer chain one at a time. So think about it like this. You have a monomer, and then another one joins, and then another one, and another one, and another one. It gets added one at a time, and the chain begins to grow. Literally, if you guys know what a chain is, I assume you do, right? This is what a chain is. It's called chain growth or addition polymerization. We just keep adding monomers to the chain. And they don't get stuck in the middle. They get stuck on the active site, which is typically at the end of the chain. Okay, so what I have underlined here is what you need to know. Okay, so monomers add on to this active site of a polymer one at a time. All right, you guys are pretty quiet today. The equation for this, and you don't need to know the equation, but this is an example of creating a polymer. Here we have a double bond, an alkene. And what happens is the double bond breaks and we add another carbon to that. And we would continue to do that over and over and over and over until we get a long carbon bond that is just an alkane. N here represents the idea that this could be, 10 carbons, or it could be 1,000 carbons. But we just keep adding ethene, or they call it, engineers usually call this ethylene, but we keep adding ethylene monomers together, and that's how we get, drum roll, polyethylene. So the reason, if you've heard of the polymer polyethylene, I don't know if it has other common names. Not really. Nah, but polyethylene, a very common plastic. It can be used for film, like plastic tubes, plastic parts, like you could imagine, like Legos. That's polyethylene. And what they do is they take this alkene and just keep reacting over and over and over. So you can kind of see how the reaction happens here. And again, don't worry, you're not going to have to write this chemical reaction. Okay, but you get ethylene and you keep adding them and adding them and adding them. You will learn more about these two terms in Chemistry 2420. Okay, don't worry about pi and sigma bonds in this course. It's not part of 1121. But honestly, guys, it would be a really good idea to keep Unit 1 notes for Chemistry 2420, because Unit 1 will really help you for 2420. This is essentially an introduction into your hydrocarbon chem. So if you don't like Unit 1, well, you might not like 2420 either, because it's all about this stuff. Okay, so these are just some examples of addition polymers. So we have chloroethene. This makes PVC, polyvinyl chloride. Propene gives us propylene. You don't need to memorize these. This is a good one. Phenylethene. So it's a aromatic bonded to like an ethene group, makes polystyrene or styrofoam. So these are just some examples of addition polymers. All right, how you guys doing so far? I only got one more thing to show you. We're going to do condensation, addition versus 4 more slides and we're going to go into chapter 2. And today I'm only going to introduce you to chapter 2. Everybody doing okay?
Yes, sir.
Thank you. And Iman, no, you don't need to know the table. Don't worry. Like basically, what I've underlined here is what you should know. You know, this would be a great multiple choice wink, wink, wink. You know, I might say which type of polymerization is when a monomer or when monomer molecules add on to the active site of a growing polymer chain, right? And you could say addition. So I'm just giving you some examples of addition polymers. You don't need to know them. But and you might be thinking like, well, why is he teaching it if it's not going to be, you know, on a test or something? But that's not the point. I just don't teach what's on the test. This is, you know, you guys are in engineering. You're going to hear about these polymers all the time. So when you hear about PVC or polystyrene, you know, in other courses, you might say, oh, yeah, it's an addition polymer. Hopefully, maybe not. I don't know. I remember when I was in university, I mean, once a course ended, I basically forgot everything from the other courses. I guess that's not completely true, but mostly true. Anyways, I'm glad you're still alive, Harold. That's always good to hear. Okay, so four more slides, and then that'll be it for this chapter. I will introduce chapter 1 today. The other type of polymerization you should know is condensation polymerization. Now, when you get into chemistry 2420, or if you do, I assume most of you will, or some of you will end up in hydrocarbon. This applies to the chemical engineer students. You will do a lab that will create a condensation polymer. So condensation polymerization is where multifunctional, so they're not simple monomers, they have functional groups. So multifunctional means functional groups. So these could be like alcohols, ketones, aldehydes. So condensation is when functional group monomers are joined together through a chemical reaction. Now, why do they call them condensation? Well, they call them condensation because these reactions produce water. So that's a really good way, wink, 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 to know the difference between addition and condensation. Okay, I have a slide before I finish chapter 1. I have a slide here that basically explains the difference between the two of them. Well, kind of. But a good way to tell the difference between addition and condensation is condensation has functional groups and water is formed. I'm not sure if all of you can remember what condensation is. It's a phase change where a gas turns into a liquid, and it's typically water. So because this reaction forms water, they call it condensation. And you can see that right here. Right, this is a byproduct of this reaction. So we actually did this in another chapter or section, esterification, right? This is an example of a condensation polymerization. And you can see we have functional groups here. We have an amine and a carboxylic acid. And again, you know, just like the last section, you don't need to know this reaction. It's just an example. And the same thing here, like Iman asked about the last table, you don't need to know this table, don't worry. But these are some examples of condensation polymers. So polyesters, keyword ester, right? An ester is a functional group. So polyester, this is, as far as I know, mostly used in clothing. You know, polyester jackets, or it's mixed with cotton. Any of you who like stretchy clothes, I do personally. They're usually blends of like cotton, polyesters, and then there's like, I want to say like spandex, but I don't know the actual name of the chemical. Polyester Amides, another functional group, is a condensation polymer. An example of this is nylon. A nylon, another form of clothing or another fabric that's blended into clothing. So these are just some examples. So the last slide I'm going to show you today, this is the end of the unit. The distinction between these two reactions was introduced in 1930, basically 1929. The big difference is an addition reaction is just between a polymer only. So you're adding, your product is just a polymer, and condensation is when you get a polymer. Now I'm talking about products. So with addition reaction, your product is just a polymer. When you do a condensation reaction, the products are a polymer and a low molecular weight compound, typically water. That's where it gets its name. Okay, so addition, you just get a polymer. Condensation, you get a polymer and water. Okay, wink, wink, wink. That's good to know. Condensation polymers form pretty slow, and it takes heat. So this is not the easiest of the reactions, and you're going to do this in CH1121. You'll do a condensation type of reaction. Oh, again, and for the people not getting or doing 2420, don't worry. This is just, if you're interested. Okay, cool. Guys, it's gonna take me a second to get into chapter 2, so you can just hang out, but if you have any questions, let me know. Chapter 2 is uploaded. There's worksheets with answer keys. I mean, there's tons of stuff there for chapter 2. I hope this is what I think it is. Uh-oh, hold on. Okay, give me 1 second here. My chapter 2 isn't what I thought it was. On my computer, I mean, there we go. Okay, give me 1 second. I'm essentially just talking to myself, I know. Okay. If this doesn't work, I can just run it off to you. No, it works. Okay, great. Okay, I'll share my screen. Oh, I didn't notice, but there are messages in the chat. Aman, you don't have to worry about the rest of the slides. Aisha, you will have a test in February. So it's a test, not a quiz. And Yasmin, yes, I'm hoping to, there's a problem with my Zoom, and I'm talking with Zoom right now to get the recordings fixed. They will definitely be up as soon as possible. A long time before your test, don't worry. But you will have a test in early February. Okay, so, well, not early, like not next week, but soon.
Okay, sir, just can you please try not to make it on the first few days of February?
It won't be, it can't be.
Because we have a test on the 28th, and then we have a test on the 1st. We have a test on the 2nd.
Yeah, no, that's okay. It cannot be then. It's impossible. We don't have enough information done.
All right, perfect.
Yeah.
Sir, please, when the test day?
I don't know, guys. There's like 3 or 4 sections of this unit. We don't know the date, because I'm working with other.
Only unit 1?
No, unit 1 and 2.
In campus, yes?
Yes, on campus.
Thank you.
No problem. And guys, yeah, I apologize. I can't give you the date, but I can give you a week's notice. We don't know the exact date because I'm teaching it. Mr. Robin is teaching it. We got to kind of see where our classes are. So don't worry, I'll let you know. You don't have to worry about it now. You should worry about your other tests, and you can worry about chemistry later. Okay, so I'll just kind of introduce Unit 2. We'll basically do this first section here. Oh, I hate these animations. Oops, I didn't mean to do that. Sorry. Okay. All right, I'm gonna have to do something a little different. My D2L is giving me trouble, but that's okay. I'll bring it up this way. Technical difficulties, as they call it. Back in the olden days, like the TV would just like break, the channel would just stop working, and it'd always pop up on the screen. Technical difficulties. I always thought that was funny. Anyways, thermochem. PowerPoints. I'm going to run it off your D2L because my PowerPoint is being real weird for me. All right, here we go. This is what I wanted. And this won't take me very long. And honestly, I think you guys might like this a little bit better than chapter 1, some of you. For Iman, this is a very math-heavy unit, so mathematics will be back. Don't worry. So the first class or two will be theory, and then we'll get into math, and you'll see some of that math in your lab this week. Okay, so here we go. Let me get started. We're wasting time here. Energy. Okay, so sorry, let me introduce this chapter. I didn't even tell you what it was called. It's called thermochemistry. Thermochemistry is exactly what it sounds like, heat chemistry. It's all related to temperature changes, heat. So when a chemical reaction gets warm or a chemical reaction gets cold, that's a thermochemical reaction. You could do one in your kitchen right now. You could take vinegar, acetic acid, baking soda, sodium hydrogen carbonate, mix them together in a glass and put your hand around the glass, and it would feel very warm. That's a chemical reaction, or a thermochemical reaction. Maybe an easier one. I don't know why I didn't say this. Lighting a candle. If you guys have candles, light it on fire. The flame is the energy product of a chemical reaction. It feels hot. So we need to talk about what energy is. Energy is the ability to do work, to do things. Maria, you'll like this chapter, and you'll like your first two labs because you will be heating and mixing chemicals. It's pretty fun. I really like this chapter. So when I say work, I mean do things. There's like kinetic energy. So, well, okay, let me link it to two things together. There's chemical energy converted into kinetic energy when you drive a vehicle. The gasoline, the hydrocarbon in your car gets combusted. It is burned. It's an exothermic reaction, and what that means is energy is released. That energy is converted into kinetic energy, which is the energy of movement, and your car moves. There's lots of different types of energy. There's like thermal energy, where you can, when you cook food, you use radiation or thermal energy. Energy is the ability to do something. Cook food, drive a car, boil water, whatever you want. This formula is what work is. But we're not talking about force in this. The only reason this formula is here is because some of you might have done this in physics, but that's physics, that's not chemistry. All right, next slide. I hate using power or D2L, but anyways. So lots of different types of energy. Like I just said, there's radiant energy, light energy. So, you go outside, you feel warmth of a sun, or you feel the warmth from light. That's radiation energy. UV rays are kind of radiant energy. Chemical energy is the energy obviously stored in chemical bonds. So when you burn a candle, you're releasing that chemical energy in the wax. Thermal energy is the energy of heat. So this is the energy you get from like a fire. And I know that's related to a candle, but what happens is the chemical energy in that candle is converted into heat or thermal energy. So they're definitely related. Wink, wink, everybody. This is definitely something you'll need to know. Great multiple choice question, you know, what type of energy is heat? I could say chemical energy, radiant energy, thermal energy. Obviously, it's thermal energy. So make sure you know that. You should like know the difference between these three types of energy. I think there might be a few more. No. Kinetic energy is another one. Let me just go back. I'm going to mention kinetic energy because a lot of you guys have done physics. That's the energy of motion. Okay, so that's another good one to know. Radiant, chemical, thermal, kinetic. Kinetic is motion or movement. All right, cool. Guys, I gotta be honest, I love this unit, so I might start getting excited in the next few classes. Because like thermochemistry is basically cooking, and that's one of my favorite things. I don't do it much, but I certainly like it. I like food, so I'll be talking about food a fair bit. Very important part of this chapter. Very, very important. Like huge. I don't know why my pen is messed up. The law of conservation of energy. The whole idea behind this chapter is the law of conservation of energy, literally. And this even applies to chapter 5, which is electrochemistry. The law of conservation of energy says that energy cannot be created or destroyed. It only changes form. You guys might have heard something similar in 1120, the law of conservation of mass. It's the same thing. Well, same wording. Mass cannot be created or destroyed. Energy cannot be created or destroyed. So what that means is when let's say, I'm sorry, I'm going to talk about food. The energy, the calories in your food. Calories, by the way, are literally a measure of energy. Calories are the same as joules. So when you eat an apple or a piece of pizza, every chemical energy, every joule, every calorie in that food that you eat is converted in some way into your body. It's not destroyed. So the reason you guys can move and we're living right now and you can talk and think and breathe and your neurons are firing and your muscles are moving is because the food that you eat is giving your body a form of energy, right? I find this stuff so interesting. I'm sorry. Electricity can be converted into light, radiant energy. A chemical reaction can be converted into kinetic energy, so like driving your car. So all the fuel in your car is converted into motion. I find this stuff interesting. All right. I really wish I had my PowerPoint, but anyways. So thermochemistry is basically the branch of chemistry that looks at heat changes in chemical reactions. Could be like we will be talking about phase changes, but it's typically in a chemical reaction. In order to talk about thermochemistry, we need to know what heat is. And this is really interesting. There's such a misconception in the general population about what heat is. People think heat and temperature are the same thing. They are not. Heat is a transfer of energy. Temperature is a measure of energy. Okay, and we'll talk a little bit about that soon. But heat is when energy moves from one object to another. So I'll give you the simplest example. You go to, Starbucks, Tim Hortons, whatever, you buy a coffee and you hold that coffee in your hands and your hands start to feel hot. That is what heat is. Okay, what's happening is the particles in the coffee are full of energy. They're moving very fast because, they have a very high temperature. And those really high energy particles in the coffee hit the slow moving particles or slower moving particles in your hand and start to heat them up. And it's all about collisions. It's really cool. We'll talk a little bit more about that in this unit, but heat is when energy moves from one object to another. So when you pick up an ice cube, why does it feel cold? Well, the hot energy in your hand, like the high kinetic energy of your hand, is transferring that to the cold ice cube. So I don't know, pretty interesting. The symbol, this always makes me laugh. If you guys could pick a symbol for heat, right? So like if you were going to pick a symbol for mass, you would say M, a symbol for velocity, V, distance, D. If you could pick a symbol for heat, what would you pick? You'd probably pick H, right? Well, no. Chemistry picks Q.
H.
Yeah, exactly. Thank you for commenting. Chemistry picked Q. There's a reason. I looked this up before. I think it might be French or something. Yeah, okay. I can answer this. But heat is not H, it's actually Q. Enthalpy, which is kind of a more scientific representation of what we're going to talk about in thermochemistry, is H. Enthalpy is H. We'll talk about that later, not today. But heat is Q. And according to the Google, this French engineer came up with it, and he called it the quantity of heat. So Q for quantity. Again, I don't know. Chemistry sometimes just makes no sense, but there you go. Heat is Q. And the units we use are J or kJ, which means joule. Oh, sorry, guys. Or kilojoule. Okay, sorry about that. So boop, joule or kilojoule. Calorie, like I said, when you guys go eat food, like tonight, if you have a snack and you look at the back of the food package and it says calories, the British and French use kilocalories. I don't know why, but calories are joules just converted. It's like miles and kilometers. Same thing, like same measurement, just different units, different magnitude. Yeah, I agree. Amount doesn't make sense. When I learned chemistry a while ago, a lot of these things confuse me. A lot of letters don't make sense. Like you could think about the mole, right? The mole. Why is the mole N? Well, I guess M was already taken. All right. Now, hold on. Let me just see how many slides are left. Oops. Okay. We might not finish this, but I'll just give me maybe 5 minutes, and that'll be it. This will kind of help anybody who hasn't done their lab yet. Oops. Okay. Sorry, I'm bouncing around. I'm just trying to see how much I have left. So one thing important to consider when you're looking at thermochemistry, and you'll see this in your labs, the lab this week, the lab next week, is system versus surroundings. The system, and like these words might not mean much to you right now, but they're very important for later. The system is what you are actually studying. So it's like the chemical reaction you're looking at. The system is what you're looking at. The surroundings is anything else that touches the system. So in my coffee cup example, the heat transfer from the coffee, well, the liquid inside the cup is the system, and the surroundings would be your hands, a thermometer, if you put a thermometer in there, the air above it. So the system is what you're studying. The surroundings is anything else around it. And that kind of makes sense in English. The word surrounding means, what is around you. Okay. Well, all of this will make sense a little bit later. So like this question here, the one on the left is a little hard to kind of picture, but the one on the right, which would you say is the system? Now, in this we have, some of you can write it down, but we have air, we have water, and we have metal. So what would you guys say, air, water, or metal? Which is the system? Yeah, metal. And actually, I'm happy that you got that, because that was not a very good question, because for me, because remember, I just told you the system is what you are studying, and what are you studying? But no, you are right. It's the metal. Usually the object involved in a chemical reaction is what we are studying. So the system is typically the chemical reaction. So yeah, the metal. This is a bad example. I'm just going to tell you this. This is a bad example, but in here, the system would be the snow, which is well, I guess the boy is transferring heat into that and melting it, and everything around him would be the surroundings. But that's not a very good example. That's a bit confusing. This is a much better example. So the metal is the system, the air and the water are surroundings. Yeah, well, that's what it is, right? It's meant to be like the snowball is kind of like the system, and the boy in the air, the atmosphere, would be the surroundings. This makes me sad. I miss snow. I didn't, when I first moved here, I didn't miss snow at all. I thought it was amazing. I was like, there's no snow. I don't have to shovel. Like, but now it's been 8 or 9 years. I miss it. Anyways, 1, 2. Okay, I want to do. Okay, I'm going to do 3 slides. I'll do them a little quick and then we're done. 3 slides. And the reason I want to do these 3 is because they'll help anybody who hasn't done the lab yet. So another thing to consider in thermochemistry is, when you're studying the system, what type of system is it? And this is honestly one of the easiest types of definitions, because the words mean exactly what you think they do. The system that's open is a system where energy can move in or out and matter can move in or out. So it's like a swimming pool. You can imagine if you had a heated swimming pool, the heat can move in or out and you can jump in. So an open system is where energy and matter can move in and out. This is very important. A closed system is where energy can move in and out, but matter cannot move out. So now let me explain that. A closed system, you can still exchange energy, but matter cannot go in or out. So what I mean by that is, if you look at this example, this is literally closed. A swimming pool is open. So like a beaker is open. An Erlenmeyer flask with the top on is closed. I mean, how simple is that? But what happens here is you can still exchange heat through this. Think of like a coffee cup. A coffee cup with the lid off, we would call open. So you could put in your milk, your sugar, and it still feels hot. You can see steam come out. But think about a coffee cup or a thermos with the lid on. You cannot put milk or sugar in, but it still feels hot when you pick it up in your hand. Right? I mean, maybe a thermos would be a bad example, but a coffee cup, you can still feel the heat in your fingers. All right, does that make sense? I hope so. Very important, wink, wink. So 2 more slides. All right, these 2 examples. So we'll skip this guy. This one, is this open or closed? What type?
Closed.
Yeah, yeah. I'm laughing because, I mean, you could show this to like, your little brother, or if you have kids, and be like, which one is closed? And it's obviously the one with the lid on it, of course. So these beakers, are these open or closed?
Open.
Open.
Yeah, exactly. Yep, exactly, guys. That's literally how easy it is. But it's really important to consider, or to know the difference between these 2, because when you change the matter, you're changing things, you're changing parts of the chemical reaction. So I know this seems a little silly, but we're going to talk more about this as the chapter goes on. This is just the introduction. Okay, finale, guys. is 2 terms, and halas, we're done. You guys did this in chemistry 1120. I kind of forgot about that, but depending on your teacher or when you did it, you might forget. When you see a temperature change, it's a sign of a chemical reaction. Do you guys remember that? So
Yeah.
signs of chemical reactions are like color changes, temperature changes, a precipitate is formed. Well, when something changes temperature, that's a thermochemical reaction. So endothermic is a term for a chemical reaction that feels cold. It absorbs heat. Endo, think of the word inside. Exothermic is a reaction that feels hot. Energy is released, so energy goes outside. So exothermic, like an explosion that feels hot. Okay, so endothermic feels cold, exothermic feels hot. And that's all I'm going to do for today. I went a little longer than I wanted. Yeah, exactly, Aman. Exactly. All right, guys, are there any questions?
Mr. Mark,
Yes.
how I can download these slides?